The problem with most deep learning systems isn't that they're wrong, it's that they're confidently wrong. In high-stakes domains, we don't just need predictions. We need models that know when they don't know. Hi everyone, welcome back. This episode was created by the research team at TeraSystemsAI. Today, we're exploring how to train Bayesian neural networks at scale using variational inference and Monte Carlo Dropout. The same uncertainty-aware techniques we deploy in real production systems across healthcare, finance, and other mission-critical environments. This episode is based on our long-form blog post, linked below. We'll go from the why of Bayesian Deep Learning to the math behind variational inference, to practical PyTorch implementations and real-world deployment results. A standard neural network gives you a point prediction. A Bayesian neural network, or BNN, goes further. It places probability distributions over the weights. Here, D is your training data. W are the weights. X star is a new input, and Y star the prediction. The integral says, average predictions over all plausible weight configurations, weighted by how likely they are given the data. The catch? For modern deep networks with millions of parameters, that integral is intractable. Computing the true posterior PW/D exactly is basically impossible. Variational inference solves this by approximating the true posterior with a simpler distribution, Q, of W phi, parameterized by phi. We maximize the evidence lower bound, or ELBO. The first term encourages the model to fit the data. The second term, the KL divergence, keeps the posterior close to the prior, acting as a regularizer. Maximizing the ELBO gives us the closest Q to the true posterior in KL sense. And because this is a differentiable objective, we can use standard deep learning tools, SGD, Adam, GPUs to optimize it. There's one more ingredient we need, the reparameterization tree. Instead of sampling W directly from QWRT, we write randomness comes from E. M and S are deterministic functions of D. This lets us backpropagate to the sampling operation, making ELBO optimization feasible with standard autodiff frameworks. Let's see how this looks in practice with Bayes by Backprop. For each weight, we maintain two parameters, a mean M and a log standard deviation log S. During training, we sample weights using the reparameterization trick. Run a forward pass. Compute the negative log likelihood. Add a KL penalty between Q and the prior. Backpropagate and update BNNs. At inference time, we can either use the mean weights for a fast, deterministic prediction, or sample multiple weight configurations and average predictions to get mean predictions plus uncertainty estimates. This gives us a scalable, fully Bayesian neural network that runs on the same infrastructure as vanilla deep nets. Bayes by Backprop doubles your parameter count. M and S for every weight. If you want something simpler, Monte Carlo Dropout is a great first step. Yaringal and Zubin Garamani show that standard dropout training can be interpreted as a form of variational inference. Keep dropouts active at test time. Run multiple forward passes, and you effectively sample from an approximate posterior over functions. From these samples, you can compute the mean prediction, the epistemic uncertainty as variance across samples, the total uncertainty via predictive entropy. This works with many existing architectures and adds almost no implementation overhead. Quick comparison of Bayesian methods for deep learning. Asymptotically exact, but too slow for big networks. Great for small models and Fury. Principled variational inference. Scalable with mini batch SGD. 2x parameters. Very good calibration. This is our go-to for many production systems. Almost free to add. Works with pre-trained models. Fast. Limited posterior expressiveness, but perfect for quick uncertainty estimation. Train 5 to 10 independent networks. Excellent uncertainty, but 5 to 10x cost. Ideal when reliability is paramount and you can pay the compute. First, the KL term can dominate early in training, forcing the posterior to collapse back to the prior. Fix KL annealing. Start with a small KL weight and ramp it up. Second, storing M and S for every weight doubles memory. Solutions: mean field posteriors, low rank or structured covariances, normalizing flows where needed, or applying Bayesian inference only to final layers. Leave an earlier layers deterministic. Third, uncertainty estimation requires multiple forward passes. We mitigate this with batched sampling on GPU, adaptive sampling, fewer passes when predictions are already confident, quantization, early stopping when variance stabilizes. Let's look at the real deployment. We deployed a Bayesian neural network for medical image classification at a major healthcare provider, processing around 50,000 radiology images per day. The model didn't try to be a hero on ambiguous, low quality, or rare cases. It did what trustworthy AI should do: perform superhumanly where it's confident and differ where it's not. Uncertainty is only useful if it's calibrated. A 90% confidence prediction should be correct about 90% of the time. We use temperature scaling to calibrate logits on a validation set and reliability diagrams, plus expected calibration error to monitor calibration in production. If you're building real systems today, here's a pragmatic roadmap. Start with MC dropout on existing models. Move to Bayes by Backprop, where calibration matters. Use KL annealing for stability. Apply post-hoc calibration on a validation set. Optimize latency with batch sampling and quantization. Monitor ECE and retrain when calibration drifts. Use hybrid architectures, Bayesian last layers, deterministic backbone. If compute allows, ensemble your most critical models. Bayesian Deep Learning isn't just about pretty uncertainty plots. It's about building AI systems that know what they know what they don't know, and can communicate that clearly to human decision makers. If you'd like help deploying Bayesian uncertainty-aware AI in your organization, from medical diagnostics to financial risk modeling, reach out to us at TeraSystemsAI